Hi, today I'd like to introduce you to one of two types of line integrals that you can possibly calculate. This one I like to think of as the area of a curtain. You think about curtains hanging in front of your windows, or um, if you've ever been to a doctor's office, sometimes they'll put a curtain between two bedrooms to give privacy and so forth, or two beds that are in the same room. These curtains hang from ceilings, so I want you to think about that as we consider what these integrals are about. So let's start by, here's our x, y, z axis, our three space, and let's consider say we have some kind of surface floating above the xy plane. I'm going to call this z equals f of x comma y. And what we could do is, if we wanted to, is we could ask ourselves, what if we had a curve that did something like this? So for the time being, pretend we had a curve in the xy plane that started here. I'll call this t equals 0, and then it goes over to here until some later time t equals, I don't know, let's just say a, some value a. And we're traversing this curve. We're moving in that direction. And so what I want to consider today is, I want you to imagine that we drew like perpendicular lines that are perpendicular to the xy plane up to this surface for a whole bunch of points along curve C. Last line should be perpendicular. It should be straighter, so bear with me. I'll try. That's pretty bad, actually. I don't want to have such a hard time with it, but you'll have to be forgiving. And see, end up with something like this. And if you imagine then, what's really happening is when these things line up along the surface up above, they create another curve that's on the surface, but that curve sort of follows the surface's bendiness in a sense. Like this curve has some bends to it. It's not like a flat table by any means. So this thing that's on the surface is going to follow that curviness of the surface. And inadvertently, what it looks like I've drawn here are four little, it looks like rectangles. These I'm drawing in the bases now, and then here's the tops. They look like four little rectangles maybe, and that's how I want you to think of them. Back in the 2D world, when you first learned about integration, one of the first things your teacher probably showed you was you had a curve y equals f of x in the xy plane, and the goal was to try and estimate the area under that curve from some value a, maybe over here, to some value b, and you did it usually by breaking the area into little rectangles like this. The kind of method I'm using here is called an LRAM, a left rectangle approximation method. And you built the integral by saying, well, look, our integral looks like this. It's the integral from A to B of the heights of all these rectangles. But the heights of them are just f of A, and then over here, that height is something else. Maybe it's f of, we'll call it x1, and this is another height, f of x2, and so on down here. This one here, f of x, whatever, x7 or something. Looks like not really, that's only x5. Okay, so there you have it. And what you'd end up doing is you should take all these heights and multiplying by your widths. Your widths here are some number delta x, and you can make them all the same width, or you can use a different width if you want. And so what this integral notation means that you learn about is that you're taking all the heights, f of x, you're multiplying by a small width dx, and the integral sign means add all those up. So here's my claim. I go back to another picture that this is the exact same thing. You have a bunch of rectangles that have heights. Here's the first one, here's the height of the second one, and so forth going across. And we could find the area of each one of these rectangles and add them up. So the question is, how do we represent that as an integral? And you've got one subtle little problem here, and it is the base of these rectangles are not quite being cooperative. Because unlike in the 2D world where the bases of a rectangle are all in a straight line along the x-axis, and it's very clear that this distance is just some small change in x. That's not happening here. This change here, let's take the second rectangle and draw in that change. It's actually a change in some diagonal direction. And so what I want you to think of is there's a small change in x here. I'm going to call that dx. And then there's also a small change in y I'm going to call dy. And so the distance I really want, which I'm going to call ds, is actually the square root of the sum of the squares of those two distances I mentioned a moment ago. So it's like a little Pythagorean theorem. That's exactly what this is. Okay, there's only one subtle thing, and that is that the curve here, this green curve we're moving along, which I mentioned, we're moving in this direction, call that curve C. You want to write C in a parameterized fashion as a function of t. So when we do an example, that'll become clear. But usually what I'm saying is that we usually write this thing as dx dt squared plus dy dt squared. That's usually what happens. All right, let's try and compute an example and see how this goes. So how do these problems typically look? Here's what they usually look like. They'll give you an integral over a curve C, and they'll give you some kind of expression. This expression gives the height of the napkin, the curved surface here, this red curved object that's floating above the xy plane might have an equation something like what I wrote here. And then you'll get this notation which will say ds. Okay, that literally means those little ds's, so let's use a yellow, those little distances, those little bases of these rectangles, which we talked about how to get over here. So it turns out that's extremely important. Okay, so back to this problem. You need to know what the curve C is. In this case, C is going to be the upper half, sorry about that, of the unit circle. All right, sorry about that sloppy handwriting. Computer's being a little bit laggy on me. We know that has an equation like this. X squared plus y squared equals 1. Okay, but as I mentioned before, if you want to compute this value ds, if you want to know what that is, we need to do a little Pythagorean theorem, but it has in it a dx dt and a dy dt. So we need to get those things. And you can only do that by parameterizing the circle. So how do you parameterize the circle? It's sort of a famous parameterization. If you want to move along a unit circle like this, we're going to start here. I'm going to say this is t equals 0, and we're going to move in this direction. Then the parameterization looks like this. X of t equals cosine t. And y of t equals sine of t. Also know that if you wanted to adjust the radius in this case is 1. If you wanted these radiuses to be something else, you'd put the radius in front of the sine and the cosine here. I didn't write the 1 because it's understood that there's a 1. Okay, so let's go find ds as we learned about in the other slide. So ds is equal to the square root of dx dt squared and then dy dt squared, and then you put a little dt here at the end. Okay, so don't forget, dx dt was, I'm sorry, x of t was cosine of t and y of t was sine of t. So the derivative of cosine would be negative sine, and the derivative of sine would be cosine. So we end up with negative sine t there, and here is going to be a cosine t. All right, and this is actually a pretty fun expression because this is sine squared, this is cosine squared. So when you add them together, you just get 1. And then you take the square root of that, you get 1. So in this particular case, it's very special. ds equals dt. And it's sort of a fun thing. You could prove it. It's a quick little easy proof. But if you had any other radius, like radius 2, for example, then ds would have been 2 dt. And if you had radius 117, then ds would have been 117 dt. Okay, so now we're ready to rewrite our integral. Here we go. Our integral was the integral over the curve C, 2 plus x squared y ds. ds just equals dt. For the curve, I'm going to do 2 plus x is cosine of t, quantity squared, y is sine of t, ds is just dt. And the one last thing you need is limits of integration. Well, if we go back to that picture here, if we want to trace out this semicircle like this, t equals 0 would definitely start off where you want it to. Do think of cosine of 0. So cosine of 0 is definitely equal to 1. Sine of 0 is definitely equal to 0. So that would start at the point 1, 0 the way you wanted. If you think about the point over here, that's got to be t equals pi. And just think about cosine pi is -1 and sine of pi is 0. So that's doing what we want. So that becomes, those become the limits for our integral. This is going to be 0 and this is going to be pi. Okay, so now we're ready to integrate. If we're just careful about this, the antiderivative of 2 would be 2t. The antiderivative of this thing, well, I think of this as like a chain rule in reverse. We have the cosine t squared, and its derivative is out here as a sine of t. So we must have had a 1/3, in parentheses here, cosine t cubed. If you take the derivative of 1/3 cosine t cubed, the 3 will come down in front and cancel the 1/3. So that'll give you 1. You'll have cosine t squared, and then you'd end up multiplying by a negative sine t because of chain rule, right? There's a little inside function there. But we're missing the negative in this expression. So what I mean is if we look up here, for example, let's use a different color for a minute. If I just look at this expression, you'll notice that there's a plus sign. So that means there must have been a negative here to cancel that negative sign when it pops out at the end. All right, and we're just about there. We just have to evaluate this now from 0 to pi. That's not so bad. If we plug in pi, we get 2 pi minus the cosine of pi is -1. This is 1/3 times -1 cubed. And then if we plug in 0, we'll get 2 times 0 is 0, minus 1/3 cosine of 0 is 1. And we're going to cube that. Okay. So what happens here? We get 2 pi. And if you're just careful with your negatives, this becomes positive 1/3. And you know that because -1/3 cubed is -1 times -1/3 is +1/3. And then over here, you have a negative times a negative, which is a positive, and times +1 cubed is just going to stay whatever sign it was. So you end up another plus 1/3. So I guess the most compact way to write this is you could write 2 pi plus 2/3. Okay, that's it. You found the area of some kind of curtain hanging down from some surface, which I didn't even attempt to draw, by the way, just so we're clear. I never attempted to draw that, so I'm not quite sure what it looks like. Anyway, thanks for watching, and I will see you in another video.